All right, can we talk models into seeing the world differently? Hi, everyone. My name is Michael Miller, and I'm with the rest of Group 10, presenting this paper by Paul Gavrikov et al. It was published for ICLR 2025 and currently has 0 citations because it's new. So let's begin with the idea of visual cues in object classification. Humans have evolved over time to make object decisions, classifications, based on the shape of the object they're looking at. This is a well-known phenomenon, and it's present in games such as Who's That Pokemon and stuff like that. Machine learning models, however, are the opposite, or are different. Instead of shape, often CV classifiers such as CNNs tend to classify objects based off of their texture, such as denim or skin. Our paper today is based off of a 2019 study of 97 humans and many different CNN models. When tested on images where there is something called a cue bias, where we mix the shape and texture information of the image, we find that the CNNs have a distinct texture bias versus humans. So like humans, for instance, would say that this is a car based on the shape of the image, whereas the CNNs are going to say this is a clock because of the texture information embedded in the image. More empirically, given a list of 16 different classes they can choose from, humans, seen here as red dots, typically would classify things based on the shape instead of the texture 96% of the time. The way to read this is, I'll use the pointer for the online people. Basically, this top row here is the proportion of shape-based decisions. So like saying it's a car instead of a clock. And 96% of the time, they're saying it's the shape. CV models, however, are kind of the opposite of this, where most of the times they are making classifications based off of the texture of the image. So the overall kind of question for our study today, knowing that there's a big difference between how humans and CV models are classifying these objects, is can we steer model biases towards the way humans naturally interpret objects and classify them? Well, to know if we can change that, we first have to understand where do they come from. So let's look into how to measure the bias sources. As we saw, by creating a mismatch between the texture and the shape in an image, we can determine what features a VLM is using to identify an object. So we have a data set of 1,200 images that have these swapped texture and shape informations. And basically, we're going to measure which visual cue the VLM is using to classify an object. Formally, we can take these correct answer counts to define a cue accuracy, which is basically just how often the model gets a correct prediction based off of either shape or texture. And then we can feed that into something called shape bias, which is how often the model gets a correct prediction based on shape. So did it guess either clock or car? And then we want car because that was the shape, and that's how humans would typically identify that object. So knowing how to measure, we can prepare our VLMs to actually classify the pictures in this data set. We do this 2 different ways for each model we test. The first one is through VQA, which basically we're going to ask the model a multiple choice question. There's 16 different options based off of the classes in the data set. And this is 0-shot classification, no conversation history or anything like that. Inside of this VQA instruction, here's some different prompts that the authors played with. In a ablation study, they decided that this one is the best, so they left it as the default. Now, the second way we get VLMs to classify things is just through general image captioning. So here we're prompting the model to tell us what it's looking at. It's similar to the previous task, but it doesn't have an explicit list of things to choose from. So here's some different prompts as they tested. The results were quite varied, but in an ablation test, they decided that the default one is the best to do, just because it gave the most stable results. So with our methodology set, we run an experiment on a bunch of different popular VLMs. Most of these are clip-based models, and there's also some black box models, some mixture of expert systems, et cetera. Basically, we can see these models spread out on a chart. This is the proportion of shape to texture-based classifications that they're making. So some key locations include humans at 96% shape bias, just like we saw earlier. Oh, what just happened? Oh, I had my finger on the wrong thing. Yeah, so Yeah, so on the top and the bottom, it's basically a proportion based on the decisions being made. So when it makes a correct classification, either that clock or that car like we saw, was it going for the car, which is a shape-based decision, or was it going for the clock, which is a texture-based decision? Humans, as I noted, are over here, 96% shape-based. The CLIP VITL14 encoder used by most of these models highlighted in purple is at 60% shape bias. And then the typical CNN sort of image-only classifier stands at 22% shape bias, meaning 88% of their decisions are based off of the texture in that image. So observing how these models do, we'll note that the diamond is for the multiple choice question, and the circle is for the just vague captioning task. You'll notice that some of these rows don't have diamonds in them. That's because some of the models just wouldn't answer the multiple choice questions, so we left the diamonds out. For each of these rows, a bigger horizontal gap means the Q bias strongly depends on the considered task, like VQA versus captioning task. So when they're closer together, that means the model didn't really change the bias based on what type of question it was asked. But you'll notice that all of these VLMs basically had a higher shape bias than the typical CNN, like ResNet 50, for instance. And then most of them also did better in shape bias than the encoder that they were based on, or that most of them were based on, which is that CLIP encoder. Looking at the differences a little more numerically, the shape bias of the image captioning task was typically way higher than the VQA shape bias. Here I highlighted the greater values. The accuracy, however, was typically the opposite of that, where it was more accurate in VQA than in the image captioning task, which was more general. Now, when they analyzed the image captioning results using an external LLM, they had the tool measure the average token length of the response from our VLM, as well as the ratio of how many responses only mentioned one of the possible 16 classes, and also the ratio of responses that don't really refer to any of the specific classes. This is called a generic ratio. Now, that generic ratio is pretty important because the authors did an ablation study where they removed these generic responses from the outputs of the VLMs. And they showed that the generic responses were what caused the accuracy drop for the image captioning task. You can see that when we remove the generic responses from our results pool, all of these accuracy percentages increase, and most of the shape biases improve towards the human level of 96. This teaches us that there's a bit of an issue with the generic responses from the open-ended question. So it's a good thing that the authors also analyze these VLMs with the multiple choice questions. Now, we know the models are biased towards texture instead of shape, which is where we want to be. So why? As we know, a VLM is comprised of two parts. We've got the vision encoder, and we've got the LLM that processes those vision tokens from the encoder. To analyze the encoder, the authors examined the relative difference between a VLM and its encoder in shape bias and accuracy when evaluated on these tasks. We also measured the error consistency between those two. We're using the same VQA results from before, and the encoders are evaluated just using zero-shot classification. First, we'll notice that all of the VLMs decreased in accuracy compared to the original encoders in the zero-shot classification. So it doesn't mean that they're going for shape or texture more. It just means they're getting it correct less often than the original encoder. We'll also notice that the average shape bias between all these tests doesn't provide any statistically significant change because they're all so different from each other. And this implies that there's room for the LLM to be the thing that's actually swaying the shape bias instead of the encoder itself. The authors posit that the encoder gives what's called a flexible token to the LLM, basically just meaning that it has both texture and shape information inside of it. That's kind of further proved by the error consistency, which basically assesses whether two observers systematically make errors on the same images. All of the predictions other than the shape label not related to the shape cues are counted as errors here, so that's what we're focusing on. Basically, our range is from 0 to 100%. 50% is like chance level. Yeah, they both got this wrong. But the higher an error consistency value goes, it's basically we're getting more of the same stuff consistently wrong between these two observers. In this case, between the encoder and the VLM. So the highest error consistency was 78%, which leaves at least 20% room for VLM decisions that differ from that encoder, which implies that the LLM and the text prompt further influence the shape bias beyond what the vision encoder actually provides. It's kind of funny because it's technically a vision-only bias, that cue, but the LLMs are actually what is giving a lot of the bias. Obviously, this deviation could only be possible if the encoder is giving a flexible token to the LLM. So that's why it's important that we measured this. So knowing that these vision tokens have both texture and shape information in them, we obviously know that the LLM is probably a big source of our bias. So we're going to take a look at the VQA task and try to examine where our biases come from in the LLM. If we look at these, we'll notice that all of these possible answer choices begin with a letter that's unique for each class, meaning one token that the LLM is going to produce. Basically, by softmaxing the logits for the first token our LLM produces, we can kind of get like a frequency of the confidence in each of these possible choices it could have made. Anything random was put into a separate null class, so we don't count that here. So we can basically study the sampling behavior to see how the LLMs turn these flexible tokens into a biased response. Here's an example of that. Basically, every image is going to give us some predictions. Now, we've got the correct texture and shape options here, and we'll mark those as correct answers for the purpose of this experiment. Now, what's interesting to note is that 82% of the time, the second less confident option or token in the logits had nothing to do with the conflicting cue. So it's either correct or it's incorrect down there. So taking that example, we'll plot the confidences for texture or shape across all images tested. This is basically a frequency chart for Lava Next 7 billion. The way to read this is the higher a Y value, the more often there's a prediction with that confidence, a correct prediction being texture or shape, like bear or bottles. So immediately we'll notice that there is a very low proportion of times where the model had medium confidence in one of these two values. It's more common for extremely high confidence, sitting at around 96, 98%. This is when it's rather certain that a cue is present and that it's the right one. And it's way more common for extremely low, almost zero confidence, where it doesn't think it's that cue at all. Basically, the confidence in both options is almost binary. So for instance, if we were to look at the shape, which is the blue line, it's either going to say, yes, this is a bear, or no, this is not a bear. Similarly for texture, yes, these are bottles, no, these are not bottles. And if you recall that the top two predictions were rarely ever both of them at the same time, it's kind of self-evident that these LLMs are completely disregarding one of the two cues it was given. It's given both pieces of information, but it's kind of disregarding one of them, meaning LLMs turn these flexible representations into a biased decision. If we look at the charts for 3 different models, these were chosen for how different they are from each other. It kind of generalizes. We see the same binary pattern. So the LLMs are disregarding one of the two cues based on how they were prompted. So those graphs were obviously only for 3 of the models, and you saw a lot more models earlier. They were only able to test, obviously, where the logits were available. To see if those results generalize across most of the models, we're going to look at something called the error consistency between them. So here's an example where, in the case of this bear, let's imagine that we sample from 3 models and 3 humans, and they all give a wrong answer that has nothing to do with the bear or bottles that they could have said. Model 1, 2, and 3 are going to be most likely to misclassify the same way, and human 1, 2, or 3 are less likely to misclassify in the same way. So they're getting the same things wrong, but for kind of different reasons. They show that in the paper through a heat map of the error consistency. So basically for a darker value crossing between 2 models or 2 people, there's more overlapping errors that they were making. So the errors, these 2 observers are making the same errors between each other. Notice that the error consistency between the models are very, very high compared to each other, but very different from the humans. So that means that the models were all getting similar stuff wrong to each other, just like we saw earlier, and making the same misclassifications within those examples. So Where the models got some similar thing wrong, they're misclassifying for the same reasons. That's different from when humans misclassified, as seen on the bottom half of the heat map. Here you can see that the humans also had similar error consistency to each other, but nowhere near as consistent as the VLMs were. So basically, we're pretty confident now that the source of the bias between our visual cue classifications are the LLM. Since it's the LLM and not the vision encoder, this opens up to the real meat and potatoes of the study, which is, can we steer models' biases towards human biases through language prompting?
Can you guys hear me?
Yes.
So now that we've seen how VLMs exhibit certain cues biased by default, we're gonna look at the methodology of some of them. So active prompt steering. What exactly is active prompt steering? It's basically a methodology where you change the prompts, like handcraft them or automate them, so that like instead of like pre-training the models, you like make the prompts in a way such that you tell the model on what to pick up on the images, such that for, let's say, for a user, you like ask the model to like use a shape-based prompt, right? So when you do use a shape-based prompt, what does and the VLM takes in that shape-based prompt, it gives you basically a shape-based output. Similarly, when you tell the model to make like use a texture-based prompt, it will give you a texture-based output. So now if you look at like more the details steps of the active prompt steering, how does it happen? So firstly, we're going to set a target bias. Either the target bias is going to be texture-based or shape-based. Then we will then we'll craft a prompt based on that target bias. This prompt would be something like describe the outline of the image based on its shape, or like describe like the texture you see in the image. Then you would present that to the VLM. So then then we would evaluate based on like the output, we'd evaluate what the final class is. So, and in automated prompt steering, there's an extra step, which is refinement, where after getting back like the final thing, it based on the output, you refine it and make it go through, like loop it back, and based on its performance feedback. So another methodology of this task is the image captioning. Image captioning is a much more open-ended task. It basically, based on like the image it sees, it basically asks, it like gets like the feedback back and uses that caption, and then like uses the LMM or like embedding to classify which it's going to be, either if it's texture or shape, and based on that, it's going to determine its final class. So here you can see when using like when prompted like the O1 model with like different types of prompts. Let's like here, like we ask it like in general to describe the image. It gives a long-winded outline of what the image shows. When you ask it to describe the image in short, it's much more straight to the point. It says it's a cat, and it doesn't go into much of the fluff. When you ask it to be more precise, it goes much more into the details and features of the cat. Like the cat has yellow eyes, yellow-green eyes, which it doesn't describe before. So if we look at, then like they did like an exploration of the alternate image caption prompts, they saw that when you ask it to keep it short, the generic ratio, which is like the generic text that it prompts, is like much lower when you ask it to keep it short. And like the accuracy is actually higher than when you ask it to be precise, even though like the shape bias for being precise is higher. So in general, they concluded like using a shorter prompt like would get like result in better outputs in their ablation study. So a much more detailed walkthrough of image caption is like you take the image in it and you craft a prompt around it. And then you take the output and you use like an embedding to get like the text and compare it to the class, and from which you get the final class. So for this experiment, we're gonna use the image of a cat, which is overlaid with elephant texture, as you can see over here. So this is called a cue conflict, where like the texture and like the shape of the image is different. So using this image, you get the output texture caption would be a striped cat-like figure with gray rough skin. From that, like using class embeddings, you'd get similarity scores. Here you can see that the similarity scores of a cat is like the highest with 72% and elephant with 65%. These are gotten from like LLM-based label extraction methods, which basically give you like the best shape match, which was a cat, and like the best texture match. And we determine which the final class would be based on like the highest percentage, which was like the best shape match of a cat at 70%. So now we move on to experiment 3. We already know from experiment 1 that VLMs have some baseline shape or texture bias. In experiment 2, we try to manipulate that bias using like the methods we explored before. So now we like compared these, like we have like a neutral prompt where like we just ask which option like best describes the image. And we also have other like a shape-based prompt where we ask it to best describe the shape and a texture-based prompt to best describe the texture. So like in this process, we like use the Q conflict image and ask it like to ask the model to focus on the shape, and we would get like the output as the cat. Similarly, we'd ask it to focus on the texture, and we'd get the output as the texture. The accuracy is tracked, ensuring we're not just forcing the model to like guess incorrectly. So here is like an output example output. When the O1 model was prompted with the picture of like the Q conflict cat and asked to describe the object in the image, I went on to describe that the image is like of that of a cat. It is described like the shape it's seeing, like such as like it has like a triangular head pointing upwards, etc. But it concludes that it's a cat. Whereas when you like ask it to describe like the texture of the image, it kind of like does a 180, right? So it goes on to describe, oh, it has like highly wrinkled and leathery appearance with numerous like fine lines and folds, basically concluding that this is like the texture of like a elephant. So you can see that we emphasize the shape of the model, like it tends to say cat, but when you emphasize like the texture, it tends to say like an elephant. Not only does like the model flip between these two when you like change the prompt, it almost does it like without like rarely hedging its bets. Like it doesn't like go into like, oh, you can see like the outline of the cat or like the shape texture. Like it completely goes 180. So basically, it already had like the representation already holds both the shape and texture data. What we like do is like using the prompt is like effectively choose like which route to pick up. So as you can see, like from the results of their study, that between like these like the fraction ratios at the top and below show like the fraction like of the shape versus like the texture decisions. You can see like the orange ones, which are like the texture-based output versus like the shape-based output, which is like the blue, and like the search, which is the automated steering, which is basically after you refine like the shape-based prompt multiple times. You can see like the differences is all quite a bit. Like you can see like you shape the texture base is like much more likely when you like prompt it to be texture likely. The diversion is much higher than when you do it for shape based. But and like at the two extremes, you can see like for interim 1.1, you can see like there's almost a 23.3% difference between the two extremes. And interestingly, like automated search sometimes nudges the bias even further, like than this, like the simple handcrafted prompts. So now, like with that, we like talked about like the visual cues, like we can like steer between texture and shape biases. But does this method generalize other visual cues? Now we'll like move on to like what? Oh.
Oh. Hey, hi everyone. Yeah, so like it was said, what about other types of biases? So one type of bias that the authors investigated is low frequency versus high frequency bias. So what are low frequency and high frequency components? To explain that, I'm gonna explain it through an image. So here you can see an original image, right? Just an image of a horse. And here we see the low frequency components. So low frequency components are the parts of an image where the intensity in the pixel changes slowly and smoothly, right? So you can see here that when you extract the low frequency components, it looks like a blurred out, smoothed image, And here's some image of the extracted high-frequency components. High-frequency components are the parts of the image where the pixel intensity changes rapidly and sharply. So you can see that it mostly extracts the edges, because the edges are the parts where the color of the pixel changes drastically, right? So yeah, so those are the low and high frequency components. So since they wanted to investigate other biases, the authors investigated how the biases of a model when it comes to low frequency and high frequency components, whether it's biased to making decisions based on the low frequency components of an image or based on the high frequency components of an image. So what did they do to test this, right? They have to have a data set, of course. So they created a data set of 1,200 samples. And there were 16 ImageNet superclasses. And this just means the unique classes, because each image is going to have two contradicting classes, right? But in total, it only has like 16 unique classes across the whole data set. So what they did to create each sample is they grabbed an image from one class and they extracted 30% of its low frequency components. And then they grabbed an image from another class and they extracted 70% of its high frequency components. And then they blended them together to end up with an image that whose low frequency components indicate one class and its high frequency components indicate another class. And before they blended, they converted it to grayscale and center cropped it so that it focuses more on the class of interest. Yeah, so here, as you can see in these two, here, these two are images from the data set. So if you look at the image on the left, you can see that the low frequency components come from an image that displays an airplane, and the high frequency components come from an image that displays bottles. You can see here the bottles is just edges, right? Well, practically just edges. And in this image of the right, the low frequency components come from an image that displays a beard, and the high frequency components come from an image that displays a boat. You can see the edges there and of the boat. So it has like conflicting classes. Okay. And to test whether the authors wanted to test whether they could steer the bias, the high frequency and low frequency bias of the model. So what they did is they set a default bias to increase or decrease, like to maximize or minimize, in this case, the low frequency bias. And they used a neutral prompt to maximize the bias and a prompt to minimize the bias, and they use the automated prompt search algorithm, which consists of using an LLM where you ask it, like, give me a prompt to maximize like low frequency bias or minimize low frequency bias. And once it gives you a result, you evaluate that result and feed it back to the model and ask it to give you a prompt that maximizes it further or minimizes the bias further, right? Yeah, and two models were tested for this. The two models tested were LavaNet 7 billion, like 7 billion parameters, and Intervial Chat 1.1, which contains 9 billion parameters. Okay, so here you can see the table, which are the results from the steering. If you see here, you can see that the accuracy wasn't significantly changed in comparison to the control, which is the neutral prompt. So when trying to maximize the low frequency bias and minimize the low frequency bias, the accuracy did drop a little, but it didn't. The drop wasn't statistically significant, and it even increased by a little bit for LavaNets when trying to maximize the low frequency bias. And here you can see the changes in low frequency bias. You can see that from the control, which is the neutral prompt, when using the prompt to maximize the bias, it did increase the low frequency bias in both cases. And when using the prompt to minimize the bias, it also decreased the bias in both cases. But there were only 2 cases in which the changes were statistically significant. For intern VL chat, it was when they used the prompt to maximize the bias, and for Lava Next, when they used the prompt to minimize the bias. It's when the changes were statistically significant when compared to the neutral prompt. And something that the authors noted is that they found interesting is that for their smaller model, which is Lava Next, the bias tended to be tending to be balanced, right? You can see that it is around 50%, while for intern VL, which is the larger model with 19 billion parameters, it tended to have a high frequency bias, right? Because these are smaller bias for low frequency, so higher bias for high frequency components. Yeah, so comparing the results to human biases, as we described before, the model's bias can be, the model's shape bias can be increased through language, but it still lags behind the human shape bias. As it was stated before, the human shape bias is around 96%, while for the models, the VLMs, it was a little over 70% even after steering to maximize the shape bias. And humans tend to have a low frequency bias, which is in contrast with the large intern VL model that we showed before, which in contrast has a high frequency bias instead of a low frequency bias. And when it comes to limitations of steerability on the study, we'll start with steerability. So vision steering, where you change the vision cues, affects the model bias higher than language steering. So this indicates that there are certain types of steering which have limitations when it comes to how it can affect the decision making of the model. Like the range of bias was higher when using vision steering over language steering. Steering sometimes negatively affects accuracy, right? And accuracy is a cost that you don't want to incur. So when you are steering a model's decision making using language, if it affects the accuracy too much, you want to minimize like your steering so that it doesn't affect the accuracy that much. So that's a limitation to language steering. And also when it came to texture versus shape bias, language steering tended to affect texture more. So you could increase the texture bias more than you could increase the shape bias. And this indicates that not all biases are created equal, meaning that there are certain biases that have more limitations than others when it comes to how much you can steer the model towards having those biases. And when it comes to the study, the models sometimes can have unexpected behavior, like the VLMs can refuse to answer, or for example, when he was doing image captioning, sometimes he would generate answers that couldn't be attributed to any of the competing classes. Or like the VLM, sometimes you give it very specific instructions to answer a certain way so that you can more easily extract the answer, but it doesn't follow that instruction, making it harder to like extract the answer. There is an unlimited amount of alternative prompts, right? But we can only generate so many using large language models. And since we're using, like for example, for the automatic search, prompt search, we're using an LLM, which has itself its limitations. It can refuse to answer or not follow instructions, right? Which limits the search algorithm, the search of the prompts. Yeah, so as a conclusion, yeah, humans are more biased towards shape over texture, as it was stated. We want AI to mimic human reasoning, human decision making, and thus we require VLMs to align more with human bias, right? Like we have been able to steer it, they were able to steer it towards a more human biased decision making, but still there is a gap. Vision encoders have a bias, but most of the bias is driven by the LLMs. And we can steer through language the decision-making process of the VLMs, which indicates that we can talk models into seeing the world differently because they're making a different, they're doing different decision-making process in a vision task. Yeah, for future work ideas, there are like different biases and also different modalities one can do. And here are the references. Thank you.